Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Hyderabad. In this session, we are going to study what is the revision of bending stresses of beams. The course outcome related to this topic is course outcome number 4, and it is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stresses, shear stress distributions and failures of beam sections. And the level of the Bloom taxonomy for this session is apply level. So let us begin the revision. Here, what is bending stress and what is bending stress? And what is the type of bending stress? What is the type of bending stress? Now let us begin with the question of bending stress is the normal stress which occurs when the load acts on a beam, and here and for a span it can become a throughout the span of the beam. There are various types of beams are there. The types of beams number 1, cantilever beam. The second type is simply supported beam. And the third one is overhanging beam. And fourth one is a fixed beam. These are the various types of beams. When this beam, suppose if we consider the cantilever beam, consider a cantilever beam. Consider a cantilever beam. For a cantilever beam, one end is fixed and the other end is free. On the cantilever beam, there is a point load is acting. The length of the beam is L. This point load W causes a stress in the beam that is known as a bending stress. Force W times and perpendicular distance L. The W times L is known as a bending moment. Bending moment equal to force, that is the load W times length L. That is the bending moment at a fixed point, fixed. Then what is the unit of bending moment? The unit of bending moment is Newton meter or Newton millimeter. If the length is in millimeters, it is Newton millimeter. If the length is in meters, it is Newton meter. Now, what are the types here? That is the question. What is the bending? What is the bending stress? Next, we have studied that what are the types of beams and how the bending stress occurs on your beams, over your beam. Next, what is the concept of pure bending? What is the concept of pure bending? If we consider a beam, that is overhanging beam, which is acted by a point loads at the ends, that is W and W, from the supports of length A. If you draw a shear force and bending moment diagrams for this case study, the shear force diagram comes. This is the shear force diagram, and the bending moment diagram comes in this manner. This is a bending moment diagram. Here the positive shear force and negative, but here if we consider the bending moment is varying from W to A, it is linear variation, but at this line it is a constant. Bending moment is constant for a length between two supports. So the beam is, but what is the shear force? The shear force is equal to 0. This is known as the beam is under pure bending. So pure bending means the bending moment for a span of the length of the beam, only bending moment is constant and the shear force equal to 0. But bending moment remains constant. This phenomenon is known as pure bending. So where will it occur, this pure bending? So in a weightlifting, lifters will carry their hands. Okay, when they will carry here, now the load here W and it is W, at this supporting points, between the supporting, the shear force is 0 and the bending moment is constant. So this is the application of the pure bending. So between two supports or two places, the bending moment remains constant, or this portion experiences the pure bending phenomena. Pure bending. It will experience pure bending. Now, what is the difference between bending moment and torque? What is the difference between bending moment and torque? What is the difference between bending moment and torque? So bending moment, in the case of bending moment, the force acts perpendicular to the distance. In the case of bending moment, the force acts perpendicular to the distance. This is the force acting normal to the distance. Whereas in torque, what is the torque? Torque acts, in the case of torque, the force acts parallel to the distance. That is the difference, bending moment and torque. But the units for bending moment and torque, unit is same for both bending moment and torque, that is Newton meter. But bending moment acts, the force acts perpendicular to the distance, whereas torque acts parallel to the distance. That is the difference of bending moment and torque. In this, what is the pure bending? After the pure bending concept, what is the theory of pure bending? Theory of pure bending. Theory of pure bending. Theory of pure bending in mathematical language or mathematically, sigma by y equal to m by I equal to E by R. How the pure bending concepts comes again? There is a beam is having different layers. When it is subjected to the constant bending moment on the both the sides M couple, the layer which is having the fibers experiences pure bending, which is at a distance y from the neutral axis. Is the neutral axis. When couple it is acting, this bending takes place in couples. Here, this layer experiences pure bending. How this concept came from? This concept came from overhanging beam. The supports, the couple is acting W and W at a distance A, here this side and this side. From this distance between these two experiences pure bending. W into A, bending moment M. Similarly, on the right side, W into A, that is another couple. From this, the experiences is the pure bending. That is what we have learned in pure bending concept. This portion, the span L, experiences constant bending moment or pure bending, where shear force is 0. Why we consider here? We have to investigate the variation of bending stress in over the cross section of a beam. Even though when the load is applied over the beam, the bending moment concept occurs, shear force and also buckling also takes place. But we have to investigate the bending moment, characteristics of the bending stress or bending moment variation or bending stress variation over the cross section of the beam, and we have to constrain the shear force and also buckling. So what we are studying, so that we are taking the concept of the pure bending. Now, when it is bending, when the bending moment is occurred at the ends, it bends. But the experience of the beam here it is, here inside the layer, these layers experiences compressive stresses. And the topmost layers experiences tensile stress. So the compressive stress, it experiences the compressive stress, and here it is experiences tensile stresses on the top layers. So there is a layer, and that layer that is called neutral surface doesn't experience or neither experiences tensile nor compressive. That means no stress it will experience. That layer is known as the neutral surface, where the stresses is 0. And there is a layer from the neutral axis, distance from the neutral layer, that is the y distance, that experiences, okay, there is a radius of curvature with the theta angle, that is R. So it is the layer distance from y, that is r plus y into theta. Now when the movement takes place physically, if you are bending any material or any sheet, any rod, it experiences not only stresses and also strain also experience. So that strain is normal strain. So now we will equate here from Hooke's law concept, because it acts within the elastic limit. Okay, it is not. The concept of pure bending is that it acts within the elastic limit. The beyond the elastic limit, what will happen? Immediately permanent deformation takes place. That is not a design zone. The design zone is that within the elastic limit, the load should be acted. Otherwise, if the load is acting beyond the elastic limit, that on the component, on the material, it yields the permanent deformation. Now, what is sigma? The sigma is here bending stress. What is sigma? Is the bending stress. The unit for bending stress is Newton per meter square. And y is the distance from neutral axis to the fiber. Neutral distance from neutral axis to fiber. This is the fiber. So y becomes y maximum for the topmost, either topmost layer or bottommost layers. Both are y maximum. Now, what is the unit for this? It is in meters or in millimeters. Where m, what is the m? M stands for bending moment or moment of resistance or moment of resistance. The unit for bending moment is Newton meter. What is moment of resistance? It is the resistance to deform, resistance to bend. So, the strength of the material, if the moment of resistance is high, that means it is having more strength. If it is less resistance is there, that means it is having less strength. Now, another definition, another letters. What is next one? I. I is the mass moment of inertia. Area moment of inertia. I stand for area moment of inertia. The unit for area moment of inertia is mm for 4 or meter power 4. Area moment of inertia of various sections, it is different for section to section. The another name of area moment of inertia is second moment of area. Second moment of area is known as area moment of inertia. Another name of second moment of area or area moment of inertia is moment of area. Moment of area moment of inertia. Now here another terms. What is E? Where E for modulus of elasticity. This modulus of elasticity is also known as Young's modulus. The unit for modulus of elasticity is Newton per square meters or Newton per mm square. pure bending equation sigma by y equal to m by I equal to E by R. We covered sigma, y, m, I and E. What about R? Where R is for radius of curvature. The units for radius of curvature is in terms of meters or millimeters. This equation sigma by y, m by I and E by R is theory of pure bending or pure bending equation or equation of pure bending. Why it is equation of pure bending? Because the shear force is zero. So this is the equation. Now from the equation of simple bending or pure bending equation sigma by y equal to m by I equal to E by R, if we consider the first two portions, this portion that is sigma by y equal to m by I, sigma becomes maximum, then y becomes y max. Now what is the bending moment? M equal to sigma maximum times I by y maximum. The ratio of moment of inertia to the distance of neutral axis to the fiber, the maximum distance to the topmost layer, that is y max, is known as section modulus Z. This is another formula. M equal to sigma maximum times Z, where Z is section modulus. And again, the unit for section modulus is mm cube. It is very simple. How it comes? Millimeter cube. The units for I, area moment of inertia is mm for 4 and y maximum unit is mm. Then it becomes Z units. Z unit is mm cube, where Z is the section modulus. Now here m represents the bending moment or moment of resistance to deformation or bending. This deformation to bending becomes maximum. Okay, when it becomes maximum, the Z becomes maximum. Thus Z represents section modulus represents the strength of a material. Represents the strength of a material. So there is one more term is there. The strength of the material also represents. Here, in the case of the stress strain diagram, in the case of a stress strain diagram for ductile materials, the stress, it is in Newton per meter square and the strain is unitless. This is the ultimate tensile stress. Here it is failure stress. The strength of the material, here ultimate stress represents the strength of a material. Of any material. Whereas sigma f represents the failure stress. It represents the failure stress. What is the strength of a material? That is which stress we have to consider? Is this proportional to yield point stress sigma y, or sigma f, or sigma ut, ultimate tensile stress? Which stress, what stress we have to consider? What stress represents the strength of a material? This ultimate sigma ut represents the strength of a material. Here, why it is correlating? Because the section modulus represents the strength of a material. The context of here, the section modulus, because when bending moment is high, that means the section modulus becomes high. When section modulus becomes high, it represents the strength of a material. That's why whenever we are going to calculate of any cross section of a beam for manufacturing or fabricating like benches or tables or load standing materials, the component has to bear different types of loads. What parameter we have to calculate? The section modulus parameter we have to calculate in order to identify the strength of a particular cross section or particular geometry. Now let us begin. What is the section modulus of a rectangular section? What is the section modulus of a rectangular section? Section modulus Z of a rectangular section. About here, this is the neutral axis. We are going to find out what is section modulus Z equal to I by Y maximum. What is the Y max? Distance from neutral axis to topmost layer. Here Y maximum equal to depth d by 2. Here B is in millimeters and D is in millimeters. Y maximum equal to d by 2. What about area moment of inertia about the neutral axis or parallel to the x-axis? That is B d cube by 12. Substitute here I and Y values in the formula of section modulus. Then we can see the section modulus of a rectangular section. That is B d cube by 12 I, and here Y max d by 2. Then it becomes B d cube by 12 into 2 by d. D get cancelled, d square 2 6 times. Then it becomes BD square by 6. This is the section modulus of a rectangular section. What is the unit for this? B unit is millimeter and D unit is millimeters. Then millimeters and millimeter square, it becomes millimeter cube. The unit for section modulus is millimeter cube, cubic millimeter. This is the formula for rectangular section. Suppose if we want section modulus for square section, Z of a square section. For a square section, it is all sides are same. That means in the formula of a rectangular section, if we substitute B equal to D, that is Z equal to BD square by 6. This is the formula for rectangular section. Substitute B equal to D, then what happens? D times D square by 6, that is D cube by 6. This is the formula for section modulus of a square section. and BD square by 6 is the section modulus of a rectangular section. So these are the formulas we have studied for another section. Section modulus of a circular section. If you consider the circular section having a diameter d, what is the formula for section modulus? The source formula is I by y max. What is the I value? What is the I for area moment of inertia of a circular section? That is pi d power 4 by 64. What is the y maximum? What is the y max? This is the neutral axis. What is the distance? Here it is d by 2. Substitute here. So pi d power 4 by 64. Then simplification. This is 32 times. Then it becomes pi d cube by 32. Again, what is the unit for section modulus of a circular section? Millimeter cube units. Now, Z is the section modulus. The section modulus of a circular section is pi d power 3, pi d cube by 32. So where d is the diameter, it can be in millimeters. Then the unit for this section modulus of a circular section is pi d cube by 32. So in this session, we have learned, or we discussed what is the pure concept of pure bending, what is bending stress, what is the theory of pure bending, what is the relation between moment of inertia and y maximum. That relation is known as the section modulus, and section modulus of rectangular section, section modulus of square section, and finally section modulus of circular section. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.